Okay, so good evening, and now we have done two dimensional problem. I think we have done in greater detail, and once you have mastered how to solve two dimensional problem, then you can approach three dimensional, because all the procedures remain the same, except that one dimension increases, which you have to reduce right in the beginning by assuming, instead of Fourier series in one direction, you have to assume Fourier series in two direction. Then we have also done how to solve problem or how to formulate problem by using what is called inverse method. Inverse method, these are all stress based methods, and we have seen that you get we make use of what is called stress function, and by taking, so we get one differential equation, we try to get a differential equation in terms of a stress function, and that differential equation is a standard differential equation, which for which solution methods are available, or people can have some standard techniques for solving. So these are the various approaches. Now what else falls under two dimension? We have done torsion. So now we will do, let us see how to do torsion of non-circular cross section. So torsion of non-circular. Actually, it is shaft torsion of non-circular. Actually, it is a shaft having non-circular cross section. So non-circular cross. We don't do torsion of a particular section. We do torsion of a rod having non-circular cross section. So title is not very appropriate, but anyway, this is how people write it. So this is attempted. There are two alternative ways. I mean, now we know what are the methods of approach for solution of any problem. You have, so there are, as usual, there are two alternative approaches, two approaches. One is displacement approach, and the other one is stress. Displacement means we will make use of some a priori assumptions on displacements, and similarly here stress means we will make use of a priori some assumptions on stresses, and then we will see what kind of formulation both these give you. Of course, this torsion of non-circular cross section, without making any sort of assumptions, it is very difficult to solve. So we do have to make some assumptions. See, you already know how to make use of, I mean, how we have done torsion of circular cross section. Circular cross section is done, there are some assumptions we make on the physics of the problem. If it is circular, or if it is a torque is applied, so right in the beginning we say yes, if it is a torque is applied. One is, if there is a radial line in the cross section, how does that deform? First we try to model that. What is the modeling of the radial line? Does it remain straight? Does it deform? Does, in the plane only, forget about whether. So if you take it, So, now we say yes, but then it is also, it is the whole thing is symmetric about the axis. So, whatever we do, it must be symmetrical about the axis. So, the point there is that if you take a deformation of that line after torsion is applied in some particular, let us say it becomes curvature becomes, all the lines have a curvature after torsion in one direction. Then now it should be axis symmetric about the axis. So, if a line is there and if it becomes a curvature, it forms a curvature after torque is applied in a particular, then every line must have the same curvature, all radial lines. And then if you see from the symmetry point of view, if you see from this side and this side, it should be symmetrical. Now, that is not possible if you take a curvature. Okay. So, from symmetry, because it has to be symmetrical, if you see from this side also, if a cross section goes like this, so because it can have a curvature either like this or it can be have in other way. Now, so we discard this based upon the symmetrical consideration, that now because of symmetry of the cross section, which is having about axis, everything is symmetrical. So, a line neither can be like this or can be like this, therefore, it has to remain only a straight line. So, even after torque is applied, what happens, only if this radial line is there, if torque is applied like this, so this line will just move like this. So, remains straight. Then the other physical consideration which we make in circular, okay, what happens to any point along this line? Does it go inside? Does that point come outside of the plane? Both are possible. So, if you take all the points, I mean let us say points are coming out. So, that means the cross section will bulge out. Cross section will bulge out. If it bulge out on this side, then it must bulge out even on this side, because it is symmetrical. So, that means all small elements along the length, if you take the free body diagram, after torque is applied, every cross section, everything will bulge out. But then every member, I mean everything, or it can be vice versa also, it can cave in also, it can go in. So, in every cross section, it will just go in. But then what happens, after all it is a continuous body. When you bring all the elements together, it must fit. So, if it bulge out, if one bulges out, the other one must came in, which is not possible, because symmetry requires that if this side it bulges out, then this side also it must bulge out. So, therefore, again it requires that it must remain only a plane, no warping. Warping of the cross section in circular is not possible based upon symmetrical consideration. So, this fixes all our remaining derivation. So, the line remains straight, radial line remains straight, and there is no warping. Warping means the plane goes out of plane. It can come out or it can cave in. So, that does not happen, it cannot happen. Now, here we will see what happens. So, we will take the displacement. So, a priori we will make here some simple assumptions, and let us see, because that helps us to reduce the formulation to a amenable form which can be solved. So, let us take the displacement approach. We will just take the displacement and So, you have a cross section which is then here again actually this should be dotted. If you are seeing from this side, then you will see. Okay, this is, and we are having, let us say, x, y and z. Z is this side, and torque is applied is like this, such that it goes from outside like this. So, torque is like this. Now, take this cross section . Let us say there is a line here P, which makes an angle alpha from x axis. It is a prismatic, non-circular prismatic shaft, non-circular prismatic You know what is the meaning of prismatic? Prismatic, yes. Cross section is, yes, same, constant cross section. So, this point P is there and torque is applied. So, obviously, this point P will move to some point P dash. Let us say this distance is R, OP is R, and this has moved to this P dash. Angle is between OP and this angle is theta. That is, angle between OP and OP dash is theta. So, first, so let us try to enunciate our this is quite all right. Only thing is, now we have to see what happens to point P. Yes, this P will move to P dash, whether it comes out of the plane or whether it goes in the plane, that we have to see. That means, warping takes place or not, that we have to see. And so, I think what is there is, we will just make it, that is, so that there is no confusion, because I do not remember the one. Any cross section of the twisted bar behaves as a rigid disc with respect to deformation in its own plane. that is, it retains its plane shape and size. It retains its plane shape, okay. It retains it in plane shape, not plane shape, because plane shape means no warping will be in plane shape and size during twisting. Of course, this is little. So, cross section, so I will just write in simple terms. Cross sections retains its in plane shape and size during twist. Now, what is the meaning of this? Two points in any cross section undergo longitudinal displacements, means we are assuming. So, assume that points in any cross section, that means points in any cross section, points in the cross section, in cross section undergo, points cannot undergo longitudinal displacement leading to warping of the section. No, I would not leading to warping cross section from its original flat configuration. Then what is the amount of this warping? How much this? That means we are assuming that yes, this the points undergo some longitudinal displacement. That is all he is saying. But then such warping at such movement of point displacement are proportional to the rate of twist. So, this cross section, for example, whatever the diagram that I drew on the first one, please. What is the twist here of this cross section? Theta. What is the rate of twist with respect to the length? D theta by dz. Rate of twist is d theta by dz, we will call it d theta by dz is rate of twist. So, this will be proportional, that means the movement is proportional to this quantity. See, for example, if the section is clamped, obviously, otherwise you cannot apply, at least one section has to be clamped. Then you apply a twist. Then there is no question of any movement. So, as you come, as you move, there will be d theta by dz will should go on increasing, rate of twist should go on increasing as we are coming and coming here. So, because that cross section is not having any warping, but then next warping, yes, little warping, then I think warping should increase, that is what I personally, let us see. But then in circular cross section everything was same throughout, no change. Here also let us see whether it is really, because physics says that yes, as I come away from my fixity, then the warping should go on increasing, if at all. Yes, let us see whether it happens. Anyway, these are the two assumptions that we make to simplify the. Now, P is moving. Now, if you see this diagram is okay on the side that I have done. So, can we, so you have, this is P and this is P dash. Now, if I draw a vertical line and a horizontal line from this, so what is this? This will be, and this line was originally here, this was alpha. So, this is also alpha, this is origin. So, this is 90 minus alpha. So, this one is again alpha. Is it okay diagram wise? If you drop, try to take out movement, like this. So, this is, so this can be u and this is v, vertical, this is vertical along y axis. So, whatever is along x axis, of course, plus and minus I have not yet shown, but the question is, this is your x and this is your y. So, so how much will be now? How much is this? Pp dash. Pp dash will be, Pp dash will be approximately equal to r into theta. If it is a small rotation, it is small rotation, rotation is not very large. So, r theta is the by which it has moved. So, therefore, I can set my displacement field as u equal to, and this is not exact, equal to Pp dash and sin alpha, but then this one is negative, this one is negative. So, this is, I must say here, this is the, because this point is from here to here it is moving, which is u is not going in the positive x direction. So, there is a minus here. So, and v is approximately equal to Pp dash cosine alpha. This Pp dash is r into theta. So, minus r into theta into sin alpha, and this, everything is approximate, and this is equal to r into theta into cos alpha. Therefore, here now what is r sin alpha and r cos alpha? Hmm? Please tell me what is r cos alpha and what is r sin alpha. If this is my origin, point P has a coordinate x and y. Point P, original point P has a coordinate x and y. So, what is? This is r from here to here. I mean, this is a small diagram I have drawn it here. This is radius. So, r cos alpha and r sin alpha will be what? R sin alpha. R sin alpha is this, that is y, y, positive y. Yes, this is y. R sin alpha is y. So, it is minus theta into y. Which one? Which one we are saying? I mean, we are talking of u. U. And what is v? V equal to r cosine. So, r cosine is x. R cosine is x. This. So, theta into x. So, well, this is the your geometrical, based upon the geometry of deformation, we can say that u is given by u, which is a function of. Here we cannot make any symmetry consideration. Since we cannot invoke, it is a non-symmetric cross section. Any symmetry considerations like in circular cross section, we have to use warping. And or warping means there has to be some displacement. So, W. So, W we do not know what should be W. W we are saying that W depends upon rate of twist. W is proportional to, we are saying W is proportional to rate of twist. So, let us say that W is equal to some constant, I mean sorry, some function which will be, again, see, it cannot be a constant, it will be a function of x and y, point in the cross section. So, say normally what, how do you transform a proportional sign to a equality sign? We always put a constant of proportionality, but here because it is a 3-dimensional problem, so we will have to have points can be so many. So, point P is a function of x y. So, you will have to put that constant of proportion, that is not a constant, but it is a function of x and y. Let us say some psi, which we will call warping function, multiplied by d theta by dx. Sorry, dz, very good, yes, d theta by rate of change of theta with respect to z. So, this psi is called psi is a undetermined function and is called warping function. By the way, this problem was solved by, or this formulation was given by Saint Venant. So, it is called Saint Venant, the rate of twist, this rate of twist d theta by dz, let us call it or denote it by theta dash. Just so, therefore, so we have got our now displacement, therefore, displacement field. So, we have set our displacement field, which is now quite for this problem. So, we are making assumptions only on displacement, we are starting with displacement. Such formulation where we start our formulation with displacement will not require compatibility equations, that must be kept in mind always. Any problem where you start your starting point is displacement, because you are already assuming that displacement is continuous, single value, whatever it is. So, there is no question of compatibility condition. So, directly we use strain displacement, because we always in a stress based method we will be using compatibility, not strain displacement. In a displacement based formulation we use strain displacement and not compatibility. Rest of the equations remain same. What are the rest of the equation? Equilibrium and constitutive. So, displacement field now is set right, and now displacement field is u is equal to means, see, there is some approximation here, it is not exact. Y v is equal to theta into x and w is equal to, we will write theta dash, yes, psi into theta dash into psi x. So, having got your displacement, next stage is you go to strain displacement relations. So, next is our strain epsilon x du by dx. This is exact, this is elasticity relation, and du by, yes, du by dx here. So, this will be what? 0. Du by dx will come out to be 0 as per this, yes, as per this field it will be 0, because theta is a function of z only, y, so it is 0. Epsilon y again it is this one v again 0, then third one gamma xy, or let us write epsilon z dw by dz here, epsilon z dw by dz. So, what should we do? Huh? Now, the problem comes rate of twist, whether it is a variable or constant. Huh? Rate of twist. We are assuming that theta dash is a constant. So, then this also will be 0. So, twist is there, rate of twist we can find out. So, if you take any two cross section dz same, both will be same, d theta by the difference in theta divided by dz will always be same when you go along the length. So, this one is same, then gamma xy huh? Yes. Can these be points undergo such warping displacements are proportional to rate of twist? Such warping are proportional to rate of twist. I am not very clear at this moment whether this means, but we are considering this. Yes, it is an assumption. It is an assumption. Sometimes you are not very. So, okay, what is this? Du by dy, du by dy minus theta and dv by dx. Oh, very good. So, this also 0. Yes. 4. Now, gamma xz. What is this? Du by dz. Du by dz, tell me. Theta dash y minus theta dash y. Because that we have to take minus theta dash into y and dw by dx psi d psi by psi with respect to x and partial derivative. So, theta plus theta dash d psi by dx, and that makes it theta dash d psi by dx minus y, and gamma yz dv by dz is x into theta dash dv by dz x into theta dash, and then dw by dy is plus theta dash by dy. So, only two components of strains are non-zero, only this and this. Rest all are four strain component are 0. Then next one is stress field. Within the plane, yes, within plane, yes, within the plane shear strains are 0. That means a rectangular element 90 degree will remain 90 degree as it goes. You make one, and then afterwards also the shape of that element will remain same in xy plane, but not in xz and yz plane. If you take that happens because of our we have taken warping. See, first one says simply that in plane shape, first one, any cross section in a twisted behave like a rigid disc with respect to deformation in its own plane, that is, it retains it in plane shape, in plane shape, in plane shape and size, shape and size, shape and size. But the points are moving, they are rotating, lines are rotating. So, this one, if I have a cross section and this is my original element, afterwards this line, after twist takes place, this line will go like this and like this. So, this angle and this angle, so that what will happen, my element will remain like this only. So, this one is same. It is not happening that there is a change in. So, this element size and this one is both are 90 degrees. So, this angle is 90 and this angle also is 90. Okay. So, okay. Now, stress field. Stress field, what are the stresses? Sigma x, sigma y, sigma z, tau xy, tau xz and tau yz. Sigma x, first 4 are 0, yes, first 4 will turn out to be 0. You write down the constitutive relation and you will find they will turn out to be 0. So, this will be 0, this will be 0, this will be 0 and this will be 0, and here nothing will happen except that g will come. So, it will be g theta dash del psi by del x minus y, and here it will be g theta dash del psi by del y plus x. So, we have got the stress field. So, we have made use of, we started with displacement, then we went to strain displacement, now we have got stresses. So, next thing is equilibrium. You must make use of equilibrium equation. So, next one is equilibrium. The assumptions that we have written, I just somehow I have been teaching for a long time, but then I was looking, somehow I could not locate my old notes, somewhere they have gone. So, I could not refresh my memory. Before I thought that I knew this, but then okay, the moment I will see my things it will be refreshed, but then I could not locate. But then I laid my hand on this book. This book is written by, somehow the assumptions that is written is not very clear. Both of them are from IIT Madras, K. Bhaskar and T. K. Vardhan, a very small compact book they have written. So, I thought let me take this. Okay, it does not matter. So, now equilibrium. First equilibrium equation, no body force. Is it satisfied? Here, first equilibrium equation. So, you see sigma x anyway is 0, tau y x 0, xz or zx whatever it is, zx with respect to z. Now, you please tell me this constant, these are all functions of x and y. So, this also is, so that means left hand side is completely satisfied. So, 0 equal to 0, we are getting it is identically. So, this is called identically satisfied. So, stress field is such that it is identically. Now, next one, see how do you write these equilibrium equations? If you recall the way we have derived it from the stress block, by taking the variation of stresses from left to right, from the left face to the right face, and then again from back face to the front face, similarly from bottom to top z direction. So, all these are we have added forces in, this is we have got because of we have added the forces in x direction. So, the last subscript should always be x here. So, here this what is that? What should be this? Tau? So, if you see this also, tau x y anyway is 0, sigma y sigma y also is 0, sigma y is 0 and tau xy is 0, and what is this yz? Yz is not a function of z again. So, again 0 equal to 0. So, this is also identically satisfied, and now we write the third one, tau xz by x plus tau yz tau xz by x, xz is there, yes, x will come. So, we get here g theta dash, and with respect to x, so second derivative of psi with respect to x square, and then this is y of course with respect to, so this is all plus yz by y. So, g theta dash del square psi del y square plus 0 equal to 0. So, we get g theta dash So, we got one equation. So, this is my, we have got now one governing equation. So, this is my governing equation. Psi must satisfy, my warping function must satisfy this, that it should be 0 in the domain, in the domain. So, this is my governing equation. And boundary. So, this subject to boundary condition. Boundary conditions of course on this here, on this boundary. So, we always have this in x direction, in y direction. So, let us call this is t n x, t n y, and there is also a in z direction, perpendicular to this is z direction, which is, which I cannot see, I cannot draw here, but then there is a t n z perpendicular to plane along on the surface. And we know that how do you, what are these? These are equal to what? How do you write boundary condition? By the way, simple way of writing boundary condition is stress matrix, that is sigma x, tau y x, r x y, tau z x, tau x y, sigma y, tau x y z, z y, tau x z, tau y z multiplied by in our case at any boundary, at any point, boundary is always defined by the normal, to draw a normal to it. So, normal is this, then we take two components, x direction, y direction, and but between n and z 90 degree is maintained. So, in our case here this is there, and plus the surface in this case the external surface is free of stresses, free of what you call traction. You apply torque only along the length, surface is free of traction. So, all this T and x and cosine of angle between L and Z, normal and Z, cosine 90 equal to 0. So, that is also 0 na, cosine 0 equal to 1, cosine 90 is 0. So, we are left with the boundary condition will be like this matrix so that will be what? Yes, what will you get please? This one will always be multiplied by 0 last here, whatever is here, sigma x, tau x, tau y x and tau z x, and similarly here tau x y, sigma y and tau z y, tau x z, tau y z and sigma z. So, this multiplication will always be 0. Yes, so what will you get? And plus we have this as 0 in our case. What are the quantities that are 0? This is 0, this is 0, this is 0, this is 0 and sigma z also is 0. Yes, okay, these two are. So, ultimately the first one will be identically 0. So, this gives us first line, first boundary condition will be 0 equal to 0. Second also will be 0 equal to 0. So, we are left with only one, and that is tau x z into ln x plus tau y z into ln y equal to 0. And now we know these two quantities in terms of psi, because we will have to put the boundary condition in terms of psi now. So, psi, if you substitute this, it will be what is this first one? First one is d psi by dx na, d psi by dx minus y into plus d psi by dy plus x into ln y equal to 0. So, at any point x y, you will have to satisfy this. So, this is all is. Now, one thing is remaining as far as this approach is concerned. Can you find out T? T means torque. Torque applied. Yes, how to find out this? So, you have your cross section, then you have your at any point you have a small element, at any point P, dx dy, this is point P whose coordinate is x y. So, this one is y and this one is So, in the plane you have the shear stress tau z y and tau z x. Normal to this is z. So, the shear stress acting on this element is the two components are this like this. Therefore, the torque this is the and z is coming outside x y z and z is from so x to so it will be this is torque is like this. So, T will be equal to given by tau z y multiplied by dx dy minus tau zx multiplied by dx dy, and this we have to integrate over the entire area over x and y, that will be given by torque total. See, this is why I have taken this multiplied by x, sorry multiplied by x. This is the force. This is the force multiplied by x and this is again the force multiplied by y. Stress multiplied by area into lever arm x and y. So, this is your integral and therefore, we can get our total torque. So, there is some problem. Yes, because this is the point and this is the area dx dy. What is the shear acting on this area? Shear in the plane. Shear stress acting on this plane only z, this is my plane and in y direction, this one. So, this area multiplied by stress will be the force in this direction multiplied by x is, and this will give me a torque which will be conforming to this direction. About this will give me a torque which will be in the positive z direction, while this will give me this stress multiplied by this area multiplied by dy will give you a torque in the minus z direction. So, this one is minus z direction. So, therefore, you get here this will be double integral u tau x you integrate this and you can get the total torque. Now, so this completes the displacement formulation. You can also find out the torque. Once you get, by the way, once you can get psi you will get no. How will you get psi? By solution of this equation, subject to the boundary condition this, subject to the boundary condition this. By solving this is the Laplace equation. This is Laplace equation. Laplace equation in psi. So, you solve this psi and then we know that yes, we can get this approach displacement is okay, except that this equation is nice, Laplace equation, but boundary condition is a non-homogeneous boundary condition. You have to satisfy this. So, mathematically, analytically it becomes very difficult to implement this. So, it can be done, people have been, but not very popular. This is not a very popular method and because of the boundary condition. So, this method is not very popular. See, if it was like this, that del square psi equal to 0 and then have the boundary condition psi equal to something, then but then psi is not simple. Psi is also one is there is a derivative and then we have to have all this. And then this is on the surface, on the external surface, boundary condition means. So, we have to ensure this. So, because of this not very popular, and this is Saint Venant's formulation. The one which is popular in torsion is the other one, is stress formulation, and we will see, I mean, which I will take tomorrow. That method, if you start your formulation from stress assumptions, then instead of a Laplace equation, you get a Poisson equation. So, this becomes a Poisson equation. Poisson equation means right hand side becomes non-zero. This is the difference between a. So, that becomes Poisson equation and then the boundary condition becomes very simple. It will be just satisfy the value of psi, I mean this function on the boundary, nothing else. So, there the boundary condition is very simple. So, people find it easier to solve torsion problem using that method. And well, this is theory. I think we will solve one problem, one or two problems after I complete this. Then you will get a feel of how to solve this problem. Okay. Next Saturday